Okay. Hey, what's up, everyone? Welcome to Intelligence Maxing Day 52. It's been a while since last stream, but today, hopefully, I can spend a few minutes going over some flashcards I made for class and try to refresh on some of the things that I might have forgot. So I think I'll start with probably my deep learning class, and then I'll go towards my portfolio management, and then also to the advanced financial management class. So I'll just flow through that way. Or, you know what? I think I might be able to do that. I'll just do this. Okay. I'll do all of them all at once, so it just gets random. Okay. So the first question, what years did the events of RJR Nabisco leverage buyout take place? I think that all happened in the year of 1988. Okay, and to 89. Private equity was a relatively new industry, new ideas of junk bonds and high financial leverage, or financial innovations. Okay. So give some background on LBOs and junk bonds during that time. Okay. What was the management group, and what was their role in the eventual LBO of RJR Nabisco? So the management group was this existing syndicate within RJR Nabisco at the time. I think the name speaks for itself. These guys were a group of high-level managers. So thinking of CEO, chairman of the board, vice chairman, I think the CEO at the time was F. Ross Johnson, and he was maybe one of the spearheaders of the management group, and they were the ones who actually first made a bid to take the company private. And after making that bid, that's what kind of started a snowball effect of different private equity firms and also investment banks that had investment arms or private equity arms. They started bidding for RJR Nabisco. Okay, so a good question is, how much did they, what was their starting bid? Yeah. So who were the main members of the management group? Definitely know F. Ross Johnson. He was the CEO. I think the chairman, vice chairman, I don't remember. Charles Hugel was the chairman of RJR Nabisco. F. Ross Johnson, he was the president and CEO. Edward Horgan, he was the vice chairman of RJR Nabisco. Okay. And then also the CEO of the RJ Reynolds Tobacco. I wonder if there's, okay, CEHFRJEAH. IA. Okay, so K, fridge, yeah. And also they had an investment bank. Okay. So I think the investment bank was also a pretty important part of their deal. Shearson, Lehman, Hutton at the time, I think, was maybe a investment bank that was trying to get into the private equity space. I would imagine that they don't really care too much about the equity in the business, but more so being able to lend to different prospective private equity firms that are looking to actually participate in these buyouts. I think Shearson, Lehman Hutton was more than happy to provide the financing for that. Yeah. So what is a proxy contest, and what does the word proxy mean? Okay. I think let's just start with the word proxy. I think in the context of a proxy contest, and maybe in the finance space, a proxy really is kind of like a substitute or someone acting on your behalf. And so when you have a proxy contest, you have a fight between shareholders and existing management, where maybe you have a single group of shareholders that is trying to vote against some type of, let's say, principle or structure, maybe even an appointment that the management, the board of directors wants to make. And as a proxy, these small group of shareholders will vote on your behalf in order to block whatever vote needs to be passed. Okay, let's see. Alright, there you go. Now you can see it. Okay. Okay, to use their proxy vote. Okay. Yeah, it's similar to what I was saying. Alright, let me make some edits to this. Okay. So, proxy here refers to the idea of a proxy vote where a shareholder has a representative then that votes on their behalf. This representative can be a larger shareholder, an activist investor, or even the board itself. Okay. Okay. So proxy here refers to the idea of a proxy vote, where a shareholder has a representative that votes on their behalf. Okay, and this representative can be a larger shareholder, an activist investor, or even the board itself. Okay. Okay, what is the idea of padding and what is zero padding? Okay, so this is kind of a completely switch up relating to convolutional neural networks. Okay, so the idea of padding is just being able to add new pixels or maybe just black or edges to the border of an existing image. And in this case, this can kind of expand and scale your image to higher or lower. Sorry, I think in this case it would just be higher spatial dimensions. Spatial dimensions, really, that's just a fancy word for just saying kind of the height and width of the pixel. Okay, so zero padding. I think the idea of zero padding is being able to create an image or pad your image enough so that your convolutional filter, kind of your kernel, will see every single pixel on your image. And when I say see every single pixel on your image, I believe that just means that the center of your kernel is going to pass through every single Okay, I think it actually means that every single pixel is going to be touched by your kernel at least once. By the center. Okay. I don't know how you define the center. I'll have to see. And then I think there's another case of full zero padding where I think every single point on your picture is going to be touched by every single point on your kernel. Okay. Oh, so it refers to adding enough padding so that the center will always touch each pixel. But I think the important thing is that it ensures the output dimension is the same as the input dimension. Okay. What does zero padding ensure? Okay, so in this case, I think this maybe could be a helpful image. We have a 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we have a 5 by 5 image. We pad it on all sides so it becomes 6 by 6. And then we have a 1, 2, 3, 4, 5. Okay, right, so our filter itself is a 5 by 5 filter. And I believe this probably has a stride of 1. So if we were to sorry, this is the output feature map, and then the kernel itself is a 3 by 3 filter. Okay. So in that case, let's see, we have start with here, and then we go 1, 2, 3. Wait, 1, 2, 3, 4, 5. Yep. And then 1, 2, 3, 4, 5. Right, because then we just go down one. Okay, so I think what this is, it's a kernel of size 3, a stride of 1, and then a padding of 1. That ensures that this 5 by 5 picture or maybe input is going to be the same output as a 5 by 5. Okay. What is the common operation used when applying the filter / kernel onto an image? I think this is the cross correlation. So when you're doing this convolutional neural network, kind of the big idea is that you have a small filter that looks at small points, maybe a small section of an image. And the reason you do that is because if you have an image, the pixels that are close to one another tend to be correlated in the sense that they probably have similar values. And the reason is, I think StatQuest ended up using an example of a picture of a dog or maybe a teddy bear. So you have a teddy bear itself is brown, and if you just choose a random pixel on that image, maybe a brown pixel, then chances are the pixels nearby are also going to be brown, just because a teddy bear is I guess just because the image of the teddy bear actually takes up a lot of space, and you don't represent a teddy bear by I don't know how to put this in words, but maybe big idea, pixels next to each other are close. Okay, so I think then we have this operation of the cross correlation where it's just the element by elements multiplication, and then the sum of all of those multiplications down to a single scalar or a single number. Okay, I guess you could call it a dot product between the input and the filter. We can say that the filter is convolved with the input. That's what convolution. So in this case, we have 0 times 0, 0 times 0, 0, 1 times 1, 0 times 0, 1 times 1, 0. Okay, she equals 3. What are 3 things that CNNs do to make image classification practical? Okay, first, I think I said this before, it allows you to kind of take advantage of the fact that most pixels are correlated with each other that are close by. I think second, I'm not entirely sure about the mathematics behind this, but I just remember Josh Starmer talking about how if you were to make pixels shift in the existing image, that won't throw off your entire convolutional neural network. It'll still make a decent classification if you modify the existing image. And I think maybe one of the bigger reasons why convolutional neural networks are a bit more practical than I think the traditional multi-layer perceptron or fully connected neural networks is the fact that with these multi-layer perceptrons you have these fully connected layers, and with the, I guess, amount of features you want to learn for an image, if you increase the number of layers, that quickly increases your parameters, maybe exponentially, but I just know that there's a shit ton of parameters that you have to train. Sometimes it's not super practical for people to do that on their hardwares, and so the convolutional neural networks, they actually have a simpler, more feasible calculation of the cross correlation, and then also the filter itself can take up a wider range. And at the end of the day, what you're training in the convolutional neural network is really the filter itself, not necessarily weights on different connections between neurons. Okay, so I think I'll take that for now. Okay, so what problem does a recurrent neural network solve? Give an example, contrast this with standard multi-layer perceptrons and convolutional neural networks. Okay, so I think what the recurrent neural network solves, with these kind of traditional neural networks like the multi-layer perceptron or maybe the convolutional neural network, your input is kind of standardized to a single size. So you would usually have to rescale or maybe pre-process your data to fit into your neural network itself. With an RNN, it's a way for you to kind of have any sized input to be able to use in your neural network. And the way it does this is it has I forgot maybe the technical term, but a connection between a node and then also one of the previous layers. So you kind of have this circular feedback loop that allows you to, I think, input, let's say, a sentence. You could input word by word, and then each time you make a new input to your RNN, it'll just go through the feedback loop and then going back and forth. So I think an example could be of, let's say, a sentence of words, or maybe even, I think our teacher gave an example of how RNNs are used for autofill. Maybe whenever you're texting or on Gmail, you type in a word and then it'll try to kind of fill in the rest of the word for you. Sometimes it works, sometimes it doesn't. But I think that technology itself is based on a recurrent neural network. So the basic idea is you have a word is built up of different characters. And so as you're typing in your keyboard, you're entering, let's say you're trying to write good morning. Then you put in G, so that's the first input to your recurrent neural network. And then you put in O, so that's your second input. And then I think it'll see these two inputs. It'll maybe see G, and then it'll predict the next letter, so O, and then you pass in O, and then it'll predict the next letter O, and then you pass in a D, something like that. Maybe. I think the next few images, flashcards, I could probably have some diagrams to help me understand this a bit better. Yeah, okay, so RNNs, this is probably a topic that Need a bit of work on. Okay, but definitely got the input with different sizes right. Oh, Josh Starmer provided the examples of stock data in which you try to predict the returns of stocks on different companies, but those companies have different time periods of being listed on exchange. You can use RNNs. Okay. Okay, so this is a good diagram from the StatQuest video. Basically, this kind of describes a simple RNN architecture. Okay, I think this itself is relating to the stock example where you're trying to make predictions about the stock price using time series temporal data. Alright, let's kind of break this down. Let's start with the first picture here. Okay, so I think what's going on here is you have this recurrent neural network, and then you make an input which is going to be today's price. And you have a weight here of 1.8, and then you have a sum here, and then also a bias. I think you can ignore the bias because it's 0, and then I'll pass into this activation function. And then y1 is going to be the outputs of the activation function. And then w2 is the weight that gets applied to the feedback loop. One thing to note about these recurrent neural networks is that all of these weights are the same for every single input. So you're not training new kind of layers. They're all going to be the same weights and biases. Now, I think what this allows you to do is, let's say we start with yesterday. So we input 0 for yesterday, we go through this step, then we get y1, and then we bring this back to this sum operation here. And then we then input 0 for today's price, and this will actually, okay, so this will take today times W1, same thing, and then it'll add yesterday's price influence together with today's price influence. And then it'll go through the activation function again, and then now we have a value that represents both today's and yesterday's price. So then we could input tomorrow's price, and then that will go through this neural network again, and then we will add the sum of today and yesterday's and also tomorrow's price. So I think that's kind of the big idea here. And then the reason why this portion of the network is kind of cut off is because each section or each feedback loop will give a prediction. You can choose to ignore it if it doesn't really make any sense, or you could choose to use it if you really care about what the output is going to be. Okay. No. Shit. Okay. Okay, so this is another diagram here for the same exact thing, except I think what this is called is unraveling a recurrent neural network. Pretty much the idea is that you're kind of just straight up copying and pasting each of these forward passes over and over again. And that's just illustrated by this connection here, where you're just connecting different small, in a sense, neural networks together, and you're passing in the same parameters every single time. And so you could see that yesterday's value is going to influence today's value as well. Okay. Main point here is to show that the weights of yesterday's price influences today's price. Okay, that's good. What is the main idea of long short-term memory? Okay, long short-term memory, I think, is a different type of architecture that tries to combat the effects of vanishing and exploding gradients. So with the recurrent neural networks, the process of unraveling or going through the feedback loop multiple times, if your weight is really small, then usually you kind of have this exponential decay or even an exponential explosion, because you're just multiplying your values by your weights kind of n number of times, where n is the number of feedback loops you have. So you can quickly kind of destroy or explode your gradients and your values there. I think the main idea of long short-term memory is you don't make that happen. And the way you do that is with the idea of long-term memory and then short-term memory. I think the way that our teacher described it was kind of a conveyor belt type structure, where a conveyor belt represents long-term memory, and then maybe short-term memory is kind of different workers in the factory, putting things onto the conveyor belt. But basic idea, you have these different nodes, and these nodes are pretty complex. They have 3 different gates. I think the first gate is called the forget gate. What it does at a high level is just try to calculate or determine how much of long-term memory should affect this actual node or the calculations of the node. I think the second gates could be I forgot what it's called, but I think big idea, you just try to figure out how much of the inputs should actually influence, or what part of the input should influence long-term memory. And then last gate is the output gate. I think it determines how much of the input should actually influence long-term memory. So you have how much versus what should. Yeah. Okay. Yeah, so let's save this. This is kind of hard. What is the main idea of an RNN? How do they work on a high level? Okay, so main idea of RNNs, they are neural networks that allow you to put in different sized inputs and also learn from allows you to learn from the previous inputs as well. How do they work on a high level? You have standard forward pass, but then you also have a feedback loop that allows you to create relationships between your inputs. Okay. Yeah, I think that's pretty good. So this is the thing that we had yesterday. When unrolling an RNN, what happens to the parameters? Any effects on model training? Okay, so the parameters, I think we said before, was that the weights and the biases, they're all going to be the same. You're not actually creating unique parameters for every single unraveling layer, but you're going to just have the same for every single one. I think effects on model training. So this will eventually make sure that when you're updating your weights and biases, all of the layers are going to have the same update effect. Now, I think the big problem here again is the exploding and also the vanishing gradients, where if you do have a lot of these unraveling layers, then all of your values, not all of them, but your values are likely to either explode or disappear. Okay, so yeah, this is kind of a good example of what the unraveling process looks like. So we have 3 different inputs, right? And then the eventual predicted value that we really care about is today's, or is predicting tomorrow's price using today's price. And then today's price is also influenced by the day before yesterday and then also the yesterday's price. Okay. So what does the first stage of a long short-term memory neural unit look like? So this is the forget gate or work. Okay. Yeah, this one's hard. I don't fully remember off the top of my head. So let's try to think about this. If in the neural unit you have kind of this line at the top that represents your long-term memory, and I think in order to prevent the actual vanishing of your gradients, you don't want to have any parameters or parameter multiplication, as in you don't want to have any weights multiplied to the actual value in your long-term memory. So I think all it is you're just multiplying or adding the outputs of certain activation functions into your long-term memory. Okay, so how does it do that? I think there's 2 activation functions to really think about here. One of them is the sigmoid activation function. Second is tanh. Sigmoid, taking an input, squish it between 0 and 1. Tanh, no, taking an input, squish it between -1 and 1. I think in this case with the forget gate, we're really going to care about the sigmoid function. So what I think then happens is you have an input to the neural unit. You do some type of matrix or weights multiplication. You add some bias, then you feed that into your sigmoid function. And then the output of that function will then be multiplied by the long-term memory value. And that's kind of the first step of the neural unit. And this is kind of the big idea of the forget gate. So the reason why it's called a forget gate is because the output of the actual sigmoid function is between 0 and 1. And then you could think of that as kind of a percentage of how much you should keep your long-term memory in this neural unit. And so maybe if you have a very low output, let's say just 0.01, then you only really need to keep 1% of your long-term memory in the neural unit to later influence the output gate. Let's see. Oh, shoot. Okay. Yeah. I was almost there, but I did forget kind of the another important part of short-term memory. Okay. The first stage takes in an input and existing short-term memory that is fed into a sigmoid activation. Okay, so the sigmoid function will output a number between 0 and 1, which can be interpreted as what percent? Okay. So even though this part of the long-term, short-term. Okay. So we have short-term memory and also an input into our neural unit. Okay. So big 2 things. I definitely need to remember that both long-term and short-term memory are going to be kind of conveyor belts in this neural unit. All right. I'm going to say that was pretty hard. Yeah. What is the exploding and vanishing gradient problem with RNNs? I think we talked about this before. You're unraveling your recurrent neural network a bunch of times. You have these weight multiplications that will grow or shrink your values exponentially. That'll cause some problems with your values disappearing or exploding. Okay. RNNs are exposed. Okay, so I think that's good. What does the final stage of a long short-term memory neural unit do? What is it usually referred to? How does it work? Oh, first stage. Okay, so first stage, forget gate. What is it usually referred to? How does it work? It's usually referred to... Okay, so what does it do? It kind of tries to set how much of long-term memory should be used with the new neural unit. It's usually referred to as the forget gate. How does it work? So you have short-term and long-term memory in a neural unit. Short-term memory, I think maybe is passed on through neural units to neural units, and there's a lot of matrix and weight multiplications that affect the value of this. But you take an input to the units and then also your short-term memory. You do some type of operation, usually some weight multiplication and then bias and then sum of both. Then you input that into a activation function, sigma 1 activation function. That'll kind of give you an output which really represents the percentage of long-term memory that you should keep within this neural unit. Okay. I will just delete that. It's okay. What are the two portions of the second stage in a long short-term memory neural unit? What is this commonly referred to? Oh man, alright. So I don't really remember this. The two portions of the second stage. Okay, I think at a high level, the second stage really is just how much of the input maybe should affect short-term memory, and then also how much of maybe what portion of the input should affect near short-term memory, and then how much should that portion actually affect short-term memory. Let's see. Potential long-term memory, percent of potential. Okay, so this is commonly referred to as the input gate. Alright, that was definitely hard, so I'm gonna kind of come back to that one. Okay. Oh, wow. Yeah. There's another question here that says, what is a simple, naive way to turn words into numbers, and are there problems with that? I think this has to do with the idea of word embeddings. And word embeddings really are just ways you can turn words into numbers. So neural networks are good with numbers. They're not really good with characters or strings or any type of words. So in order to actually input these words into numbers, there's different strategies to actually try to do that. So this one is asking for a simple, naive way to do it. And I remember in the StatQuest video, he gave an idea of just randomly assigning a number to a word. And the big problem with that is usually words have words that are similar. I think they're called synonyms. I kind of forgot a lot of the English stuff I learned in high school, but you have words that have similar meanings, and if you were to randomly assign different words, random numbers, then you might have this case where, let's say you're using the two words large and big, and you randomly assign big to 1000 and then large to negative 1 million. So those two numbers are drastically different, but the meaning behind the two words are very similar. And so when you're passing this into a neural network to make a classification or maybe some type of prediction, then these two inputs will have a really big difference and maybe a pretty big effect and impact on the prediction or classification. Okay, so what does StackQuest say is a better alternative to assigning words a random number to be fed into a neural network? Okay, I think his big idea was, all right, you could try to actually create a neural network to do the assignment itself. And I think the way he does that is by trying to train a neural network that will predict the next word in a sentence. So you have kind of your input vector as a one-hot encoded vector of words where the 0 represents the word isn't being passed in, and then 1 represents the word is being passed in. So I think he used the example of Gymkhana is so great, or is a good movie. Gymkhana is a good movie, maybe, as his label. So that's the sentence. Your labels are going to be sentences of words, and then your input is going to be individual words themselves. And so you kind of measure the accuracy or the performance of the neural network by comparing the inputs and then the outputs, and then whether or not that output is the next word in the sentence. So the actual embedding itself, I think, is going to be the weights for that input. So I think this will be some type of fully connected layer, and the weight itself will be, I think it'll be used for every single right, so there will be a weight for every single input, and I think that itself is going to be the actual embedding. Okay. God damn, that's a pretty complex graph. All right. Yeah. Oh, he uses softmax too to output the probability that one of the words is going to be. Okay. I will say good for now. Let's train a simple neural network to create an embedding and numerical representation for each word we want to input into your neural network. The way the network is optimized / trained is by passing in a word into the simplified neural network via one-hot encoding and trying to predict the next word. Okay. So, why are word embeddings important? They're important because it allows us to use words in neural networks by turning them into numbers. Okay. What is the advantage of using a neural network to embed words instead of randomly assigning them to a number? I think the big idea here is that if you're using a neural network to embed the words, the neural network can kind of learn the context. I think that's a word that's used commonly. But basically, context here refers to the similarities between different words and the relationships between different words as well. Position. StatQuest used the example of the sentence Troll 2 is great as a label that can help train a neural network to assign embeddings to the wording. That appears when a word is input into the model. Okay. See that? Okay, explain what's going on in this picture. What is the input? Why are there two activation functions? What does the output look like? What is this trying to do? Okay, so this is a good question to ask actually. Let's start with the input. Inputs is a vector of possible words that we're trying to embed. So troll 2 is a word, is a word, great is a word, Gymkata is a word. This is a vector that's kind of one-hot encodes these words. Then we have two activation functions. So all of these words are connected to both of these layers. So you have kind of these two node layer that's fully connected. The reason why there are two activations, I think, is so that you can have multiple embeddings for the same word, and then maybe you could kind of take a weighted average of this. I'm not entirely sure on that. Okay, what does the output look like? So the output here is going to be first of this input layer, and then also this hidden layer here is going to be kind of this result of doing some multiplications and activations, additions. Then you take the actual scalar here and then you input it into the softmax function, which gives you the probability of the next word that's going to appear in the sentence. So the output is kind of a list of probabilities, which the highest probability is going to be the predicted word that appears after the input word. Okay, what is this trying to do? So this is a standard word embedding model where you're trying to learn the context or maybe trying to learn the embeddings, the numerical representation of words based on the predicted outputs of our model, and being able to predict the next word that appears in a sentence. Okay. That embeds the words troll 2 is great, Gymkata. Okay, that's pretty simple. Person running wants to associate the code words with two values.
Jimmy B's not there, but that's really our artist. So, but I can't do nothing about that. You know what I'm saying? At the end of the day, you know what I'm saying? Things don't go like really. So you worry about something?
Okay. In the picture above, the input to the network is the word Gymkata, and the output is one from. Okay, I think that's pretty good. What was the management group? Okay, I think I'm probably gonna head out in like 2 minutes. Gotta go use the bathroom, and then after that, probably continue, and then get some lunch before my class starts. But what was the management group, and what was their role in the eventual leverage buyout of RJR and Nabisco? What was their starting bid? Management group, they were the existing management group, or the managers, the C-suite executives of RJR and Nabisco. They were the first ones to actually promote the idea of taking the company private, and their starting bid, was around $17 billion. Okay. What years did the events of RJR and Nabisco take place? Give some background on LBOs and junk bonds during the time. So, years 1988 to 1989. LBOs at the time, they were kind of this new financial invention. Really hadn't been too much activity as compared to today. Kind of the big movers of the leverage buyout is KKR, Kohlberg, Kravis, and Roberts. These guys were the main players at the time and really kind of the originators of the leverage buyout. Junk bonds were also a popular financial tool, and this, I think, was also a pretty recent innovation at the time. Just being able to issue bonds or issue debt for really risky companies with low credit ratings that probably would default, and so you would get a really high credit premium or credit spread for taking on that risk. Okay. Who are the main members of the management group? Okay, F. Ross Johnson, President, CEO, Chairman Charles E. Hugel, and then the Vice Chairman and also CEO of R.J. Reynolds. It was so CEH. I know his last name starts with an H. Charles E. Hugel, something A.H. Edward A. Horgan. Okay. Oh, and then Shearson. Investment. Who was their investment bank? I keep forgetting about that. Alright, so we're gonna use the bathroom now, and then I will continue the stream, hopefully, in about 20 or so minutes. So, thanks for tuning into this one. Catch you guys on the next one.